And now we're in really good shape because there's just whoops. Okay, well now we're in good shape because this isotope just was totally supported at the -8 level. Our band was up there at -5. So once we're finished isotoping this, we just slide the band down, and now we're ready to just cancel the critical points. And so right, so this is this is critical point. So anyway, I can try to explain in this case how to cancel a critical point of index 0 and critical point of index 1. And in a similar manner, you can cancel all the critical points of index 0 with the critical points coming from the bands at -6, and the bands at +6 can cancel all the critical points of critical point of index 1, cancel the critical points of index 2. So that's sort of an outline of this four-dimensional light bulb theorem. So in these last couple minutes, just share several applications. And one is, suppose we're in S2 cross D2, and you just have a properly embedded disk. Then the boundary of this disk is just a curve in S2 cross S1. If this curve in S2 cross S1 is isotopic to the standard vertical curve, then in fact this disk is isotopic to the standard disk. So disk in S2 cross S1 is standard if only a disk in S2 cross D2 is standard if only a boundary standard. And using that, I can show that disk 0 of S2 cross D2 modulo disk 0 D4, that's trivial. So in other words, if you have a diffeomorphism of S2 cross D2, then you can isotope it. Well, orientation preserving diffeomorphism, then you can isotope it so that so the identity extends within some small ball. And so the restriction of small balls, well, that corresponds to an element of disk D4, and so there's another question whether the homotopy is isotope for diffeomorphisms of a 4 ball that picks the boundary pointwards. So, and here's another application, which is that if you have two smooth disks in the fluorosphere, which have the same boundary, then you can isotope one to the other, fixing the boundary pointwise. As I mentioned, the Cerf-Palais theorem said that disks are unique on the isotopy, but there you have to somehow sweep it in and sweep it out. But you can now do this just fixing the boundary pointwise. So let me just try to put this theorem in a little different context. So in one dimension lower, that is, if you have an arc in, say, the 4 sphere, so that there's these two endpoints. Of course, S4 is simply connected, so you can homotop that arc to be just a standard straight arc between these 2 points. But we know that for one complex is a 4 manifold homotopy implies isotopy. So which is what I call general position. So this theorem for arcs in S4, that's homotopy implies isotopy. This is the theorem for disks, 2 disks in S4. And now if you promote this to 3 disks in S4, that is, if you have embedded 3 disk, so embedded 3 ball whose boundary is the standard 3 ball, if you could isotope that to the standard 3 ball using the boundary, well, then that would imply the 4-dimensional Shelby theorem. So actually, I think this is actually what I said. If you homotop a 3 ball to the standard relative to the fixing point, I believe it's a stronger, perhaps equivalent, but I think it's actually stronger, more difficult problem. But certainly it's not a selfish problem. Anyway, thank you for your attention. So if the tip of the ball was connected, then any diffeomorphism of S2 cross D2 would be isotopic to identity, properly isotopic to identity. Mapping creates groupings, diffeomorphism modulo homotopy. So I'm just saying if it's homotopic to identity, that's modulo disk D4 homotopic to identity plus isotopic to identity. That's top range. Not trivial D2. So, I think that's also correct. Actually, there's a stronger theorem that you mentioned, actually, which is Hastert-free, which is that if you have two, so the light bulb theorem is conditioned for a sphere to be isotopic to standard sphere in particular space. But in general, if you have two spheres which intersect a third common 2 sphere exactly at a point, and those two spheres, so S1 and say R1 and R2 intersect G in a single point, and R1 and R2 are homotopic, and pi 1 of the 4 manifold has no 2 torsion, then I'm claiming that I can prove that that case homotopy implies isotopy. Thank you for correcting this. This six transfer sphere has a trivial normal bundle. Trivial normal bundle is crucial. It's a fantastic question, which is to answer the same question for CP2. If you have 2 sphere that intersect CP2 standard in one point, is it isotopic to the standard thing and first thing? And that's thank you for the trivial normal bundles essential here. So we tell me this is really important. Just this is a positive result. So somehow other side against it, I have question. And this identify the borderline with the design so that you have a negative result for this positive result. Yeah, that's a great question, which is that, as you all know, there are 4 dimensions of these spectaculars. Maybe because this is JDG Conference, I must mention it, but JDG, I think the first paper I wrote was actually published in JDG. It was something like 33 years ago, so kind of one third of the whole history. And probably I have four papers I think probably published in JDG. But honestly speaking, all my papers published in JDG are on immediate geometry. And after I turned to game theory and simple geometry, I still not published any paper in JDG. It might be that the paper have a bit lower quality, but a possible excuse is that after I'm working on this simple geometry, the paper I like is longer and longer. I remember that something 10 years ago we were working on this Japan theory papers. Yeah, finally suggested as a possibility to do some readings to JDG. But then when we finished it, we found it is something like 1,000 pages. A little bit too lengthy to publish in JDG. We will finally publish in international press, but not in JDG. So maybe something that I need to try to simplify through for the podcast so that it fits inside of JDG. But anyway, so I want to talk about equivariance,